Okay, today we'll talk about the fins. Fin is a very common, useful, very common used device we use in industry, people use to transfer heat. Okay. You will see fin in many different devices when you generate heat. I think the common choice is to use fins to transfer heat, and it's cheap and efficient, and it's easy to make. Okay, so it's very common used. So it is a conduction convection system. Let me send you a figure. Okay, it's in textbook. I'm bad on drawing, especially on this whiteboard. So I take a picture of the figure. Actually, it's figure 2.9, okay, in the textbook. That's the geometry of the fin. Okay, let me send it to you first. Okay, then you can take a look. We'll talk about that geometry. Okay. Hold on, let me find the file. Okay. Okay, I sent it to you. Please take a look. This is a typical classic fin geometry, right? For a base material, so you add a fin material there because you know why it can enhance heat transfer. So it exposes more area to the surroundings. Okay, you know the both in the convection heat transfer equation, HA delta T, right? So of course, convection heat transfer coefficient matters. Okay, the bigger the better. You open a fan, blow wind to it. Yeah, your H increases. You enhance the heat transfer. Also, the area. If the surface area exposed to the air increases, your heat transfer will also increase. Okay, so that's the mechanism for install a fin on a surface and to increase the surface area, okay, to enhance heat transfer. Okay, so let me share my screen with you. Okay, let's continue on this. Fin heat transfer. Okay, hold on. Let me still keep the. Okay, let me put a pen. Okay. So it is a conduction convection problem. If you look at the figure, you will see, hey, in the base, the hot temperature, right? And the heat goes through this fin material. So inside the fin material, it is conduction. Okay. It is conduction inside the fin material. Look at that. It's a Q, right? So Q has direction. So it's going from the left to right on the figure. Okay. Also from the fin surface, as well as the original wall surface of the material. Sure, they're both exposed to air. So they will have heat transfer. Okay, convection heat transfer. So the convection heat transfer of the fin is it's from the surface of the fin. Okay, obviously the surface area increase a lot comparing to originally set up without the fin, right? So that's the situation. So hopefully heat transfer will be enhanced. So the equation derivation, let's skip that. Let me give you the equation. Equation 2.38, that's the general equation for temperature distribution inside the fin, right? So the second order derivative, because this we have the conduction, as we discussed before, conduction, it's dt squared of dx squared, okay? Minus HP over Ka T minus T infinite equals 0. So this is the simplified equation for the microfin problem. Okay, this is the equation. This is not a solution, right? Obviously, it's a differential equation. It's not a solution. Okay, so you don't need to worry about how to solve it. I'm gonna tell you the solution to be used on different situations. But I have to introduce the equation for you first. Okay, so by convention, okay, we don't like to see T minus T infinite. Oh, by the way, what is T infinite? That's the ambient temperature. Okay, temperature of the air, of the surrounding. Okay, for the convection, right? So by convention, people like to introduce a relative temperature. Let's say theta. This is theta. It's not the Q, heat transfer rate, right? Theta. We define it as T minus T infinite. Okay, so it's a relative temperature. Many of you in my fluids class, right? We talk about the pressure. Remember, we use what? Gauge pressure. The right gauge pressure is also a relative pressure. It referenced with the atmospheric pressure. So everything above atmospheric pressure is positive. If it's lower than atmospheric pressure, it will be negative gauge pressure, right? Same thing, same idea. So here in temperature, for any individual problem, the ambient temperature, we treat it as a reference temperature. So this theta is the difference between your temperature inside the thing, the difference between the temperature inside the thin material and the ambient temperature. Okay, it's a relative temperature. This is nothing fancy here. It's just a relative temperature. Okay, it's convention. It makes the equation look a little bit simpler. Okay, so this general equation, this governing equation become d theta square over dx square. So it doesn't change, right? See, T infinite is a constant. When you take a derivative, it's gone. Okay, so the form is still the same. HP over Ka, these are the coefficients and the theta. Okay, here is a little bit simpler. Instead of T minus T infinite, we have a theta to replace it. Okay, it look a little bit better equation-wise. Okay, that's convention. Okay. Okay, so you can calculate for theta instead of T. Okay, in this equation, basically this is equation 2.30b. Okay, so this equation is solvable. Okay, it's okay. Okay, and we solve for theta instead of T. Then we can convert into temperature if you want to know exactly the temperature is, right? It's just if you find the theta plus the ambient temperature, that's your temperature inside the thing. Okay. Is that okay? Any questions so far? Okay. Again, be familiar with this type of differential equation. Okay. Okay. So temperature is not a constant. T is an unknown, right? It's a variable here. Okay. Look at the graph I sent you. Okay. Temperature, this is T, is the temperature inside the thing, and it changes with X. Okay, it is a 1D problem. We simplify into 1D. It's not purely 1D, sure. It's, of course, you have the heat transfer go through the side, you have temperature change along the Y direction or Z direction, sure, it is. But we simplify it, okay? We don't want to start with too complicated equation. If you make a 3D equation, there's no way to solve it, okay? So we simplify it and say, hey, along the vertical direction, Y direction and Z direction, the temperature doesn't change along that direction. It only changes along X direction. Okay, that's the assumption we make. Okay, so that leads to this equation. Again, in engineering, we have to stay with less perfect situation, right? We want to have solution. Yeah, have a solution better than no solution. That's always my philosophy. Okay, we need to produce, okay, make stuff. So that's the equation, 1D conduction convection problem. Okay, this is a microfin. in that sense, because of this assumption, the thing has to be thin, very thin, and comparing the thickness comparing to the length has to be small because we said it's 1D. Okay, if you have a similar size and y, x and y, then this is not a thing. Then this equation won't satisfy because you have heat transfer along the other direction. Okay, so this is the equation. Then, you know, the goal is we need to solve it. Any question here? You know those letters? I think look at the drawing I send you to. A is the cross-sectional area. Okay. So what is a P? P is a parameter of this, right? So and the H is the convection heat transfer coefficient. K is the thermal conductivity, right? Okay, and something not in the equation is the length L, and the Z is the other dimension. Okay, and the thickness of the thing is what? You use the letter T. Okay, we will see it later. Okay, you probably need to apply T for something. Okay. The P, make sure you understand, it's the parameter of that little band. You mark the dark color in the drawing. Okay. So P dx, look at what's on the drawing. It said P dx, right? What is the P dx? The parameter times dx. So it's actually the total surface area of that band. Okay. So that's dq convection. So the convection heat transfer through this area. Okay, this gray color area. Okay, HA delta T still. Okay, so this is the equation. So the solutions, you have different solutions based on the boundary conditions. There are three different types of boundary conditions for this differential equation. Again, this is the differential equation. When you solve it, you need the boundary conditions, right? If you have the D, I think in calculus, probably you talk a little bit about this, okay? Differential equation will be solving, in that class, we're solving those differential equations. For all the differential equations, you need the boundary conditions to solve, okay? So three types of boundary conditions. Okay, case one is that it's very, very long. Very long. Okay. Very long thing. What happens to very long thing? I barely see a very long thing in industry, in any of the application. It's almost, it's long enough, very, very long that at the end of the thing, the temperature is just the same as the surrounding temperature. So think about this. Look at the geometry. Hey, the heat transfer from the base to the tip, right? Then it loses heat through the side, through the surrounding, through the convection. Okay. So you get a less and less heat when you go through the x direction. Right? You get less and less heat. Okay. At the end, if it's very, very long, infinitely long, at the end, there's nothing. No heat left. All the heat has to be transferred out through the convection from the side. Okay, that makes sense? So then if it's very long, at the end of the thing, okay, the temperature is just the surrounding. Okay. Case one is a case like a theoretical, case. That's it's easy to solve for this equation, but I barely see any real-time case like this. Very long thing. Okay. Case two, it has a finite length. Okay. Finite length at the end, it's just convection. So at the final length, there's always some heat left when the heat flow reach to the tip. That makes sense? So at the end, it's a convection boundary condition. Okay, but by the way, this is the 1D equation, right? Differential equation. So your boundary condition will be at the x direction, at the end of the x direction. That's your boundary condition, right? So at the end of the x direction in this drawing, you can see at the end of the x direction is the tip, is the ending phase, okay, of the thing. Okay, so the second type of boundary condition is when thing is final length, then the heat, you know, there's some heat left when you reach to the end. So there will be a convection heat transfer to the end. Okay, there's a second type. The third type, it's also finite length, but the tip is insulated. Okay, the tip is insulated. So that's 2 and 3. So basically there's some heat flow goes out in the tip, but in the type 3, there's basically no heat flow going out. Okay, it's a dt dx equal to 0 at the end. There are small changes between 2 and 3. If the thing is, you know, not too short, if the thing is still long, it's not very long like a case 1. If the thing is reasonably long, then the difference between 2 and 3 is it's not that much. Okay, because at the end, the thing tip usually is small. You have small area, right? Then in the for a certain length of the thing at the end, then not much energy left, not much heat left. Insulated means that totally nothing left at the end. Okay, but with the finite length. Okay, so it forced to stop the heat transfer at the end, and then some of the heat will force them to going out through the side. Okay, so there are some difference between case 2 and case 3. Okay, in certain situation we can in industry, in certain application with reasonable length, 2 and 3 results should be similar. Okay, but case 2 look the result. I'm sure I'm going to show you the equation, the solution. Case 2, the result look much more complicated than case 3. Okay, so case 3 is a little bit simple in the solution. So sometimes people use case 2 for more often. Okay. Okay, the solutions. Okay, case 1. The 2 types of solution I try to mention here. One is, of course, the temperature, the theta, right? Remember what is theta? Theta is T minus T infinite, okay? So one is theta, which is T, temperature, okay? This temperature distribution inside the thing. The other solution is the heat transfer rate, total heat transfer going through the side of the thing, okay? Total heat loss, basically, okay? Total heat transfer rate, Q, basically. So case 1, theta over theta 0. Okay. What is theta 0? Okay, let me write it one more time. Theta means T minus T infinite, which is the ambient temperature, relative temperature, okay? Theta 0 means T0 minus T infinite. Okay. T0 minus T infinite. So T0, oh, okay, probably I didn't mention T0. T0 is the base temperature. Okay, 0 means the starting point of the x-axis. Okay, so it is 0. Okay, it is starting temperature, the base temperature. Okay. So it is equals to E negative mx. Okay, let's put it complicated, it seems like. Okay, E, okay, so you know E, right? In the power is negative mx. So what is m? So m is defined as somewhere in the textbook, m is defined as, let me see where it is. Okay, m is defined as this. M equals to square root of, so m squared equals to HP divided by K8. Okay, it's property. Seems like it's property. Okay. So that's a solution for that. Okay. Actually, I didn't write it down. The general equation, kind of like a. Let me write it on the previous page. I missed that. I think I probably want to give it to in case some of you are interested. Okay, the solution without applying this boundary condition, the solution is equation 2.31. Theta, so this is the equation for theta, right? Theta equals C1 E negative mx plus C2 E mx. Okay, so that's a solution here. So m is defined as HP divided by Ka. I think m squared is defined by that. HP divided by K, because this is HP Ka, right? So sometimes people just use this, replace it by m squared. Okay. Okay, sometimes you see the textbook, you see the equation d theta square over dx square minus m square theta equals to 0. Okay, so for simplification on writing. Okay, so this is the general solution for this differential equation. Okay, why you have C1 and C2, two coefficients there? Because you haven't applied the boundary condition yet. Okay, you basically need two boundary conditions for each type, right? You need the starting condition and the ending condition for that thing, right? So it's d theta square over dx second order derivative. So you will need two boundary conditions to solve this differential equation. Okay, so each type, this is each case, case 1, case 2, case 3. It's just tell you the ending condition, but there's always has a starting condition, which is just T0, right? Temperature. It's the base. Okay. So because of second derivative, two boundary condition, you will have two coefficients before you apply boundary condition C1 and C2. Okay, so that's a general solution for this. So when you apply the case 1 condition, then the solution becomes this. Okay. Well, that's good, because m is properties, right? HK, they are property. P is the parameter. A is the cross-section area. So you should be able to get m pretty straightforward. So the temperature theta or T is a function of x. Okay. Seems like when x increases, the temperature, the theta increase or decrease? It's a negative power, right? It's 1 over EMX. So when x increases, the temperature is going to decrease. That makes sense, right? You lose heat to the surrounding. Okay, when x increases to the end of the thing, the temperature should decrease. Okay, so this is a temperature distribution inside the thing for case 1 type of condition. And there's a Q. How about the Q?
Can you check your waiting room?
I think nobody in the waiting room right now. I just let one student come in.
Okay.
Yeah, thank you. And the Q, this is the temperature, right? The total Q loss. So that's important knowledge to know. So total Q loss through the side of the thing to the surrounding, that's how much heat you can transfer with the thing, right? That's the goal, right? That's the industry application for thing. We just want to transfer heat from the base to the surroundings, okay? More heat will be transferred, will be better. So the total heat transfer rate Q, total, that's total, okay? For case 1 is that's equation 2.35. H P K A in the square root times theta 0. So theta 0 is the boundary condition. It's not, we know, right? T0. Okay. So that's the total heat loss for case 1. Temperature and the Q. Okay. Did everybody follow me? I don't give you the example yet. I'm just explaining these equations. Is that good? Understandable? Okay. This is the general equation, right? So this is a general solution for that equation for the thing. Okay. Then with the boundary condition, case 1, so you get a temperature distribution inside the thing. That's a solution for T. Then this is a solution for Q, total heat loss through the thing. Okay. Any question, please jump in. Okay, please understand these equations before you can apply these equations and solution to practical problems, okay? To me, heat transfer to this point, undergraduate heat transfer is not really difficult because we skipped all the calculation part, the calculate how to solve the differential equation into, so we just directly get the solution, then we just apply it to the problem, okay? So basically you just, for each problem, when you look at the problem statement, you want to pick a case, then apply the solution, that's it. Okay, not too difficult. Case 2. Case 2, look more complicated. Again, theta over theta 0. That's much, much longer. It is equation 2.30, equation 2.34. It's E, right? It's related to the cosine sign, but it's cosh here. Anybody know what is cosh? It's hyperbolic cosine, right? Okay, so look at the expression on the textbook. Cosh x equals to ex plus e negative x divided by 2. Okay, so cosh m L minus x, okay, plus h over mk sinh, okay, sinh is e to the power of x minus e to the power of negative x divided by 2. Okay, I don't know, did you learn that in the trigonometry? L minus x. Okay, you're dealing with those equations, huh? This is the college level, right? In the denominator is cosh ml plus h over mk sinh. Sinh ml. Okay, did I pronounce it right? Does it call cosh and the sinh? I know that's how I always call it. I may be wrong. Anybody?
Whatever you want to call it, Doctor.
Whatever I want to call it. That's a good attitude. Okay, but don't get scared about these things. Okay, it's okay. You're a college student. You should be able to handle, right? It's just a little bit longer. You know, you find the definition of cosh and sinh, and then it's just tedious, very tedious to substitute the numbers. Okay, you even putting the number there to do that actual calculation is not a simple task, right? But I believe in you. You guys are juniors, right? You go through all those tough classes through here, you should be good enough, okay? Okay, very long, okay. So,
Dr. Sang,
yeah.
so whenever you say cosh m times L minus X, is that
No, it's not times, it's cosh,
of?
ML minus X is all inside the cosh.
Okay,
Okay,
so
okay.
that's the whole argument.
Yeah. Good question. You see, I should put the parentheses there, but the equation look too complicated. Okay, the textbook it didn't put the parentheses there. You know, to group M times L minus X. These are all inside the cosh. Okay, that's a good question. I think strictly speaking, the way the textbook write like this is not very correct. You will think it's a cosh M, right? Then times multiplied by L minus X. Okay, it's not like that. Okay. Okay. Did everybody hear this? This is a very important question he asked. Just make sure. Okay, everyone's like this. You should put a parenthesis there. Okay, if I was the author of the textbook, I'll put it there. Okay. So for every term, it's like this. But it look messy when you write like this, right? Okay, but that's the correct way to write. Okay. Then the Q for case 2. The Q, that's look even worse. Okay. H, P, K, A times T, it's theta 0. Okay. Okay. Then multiply by, I have to write in the next line. Okay. Sinh ML plus H over M K cosh ML. I'm writing the correct way. Okay. Cosh ML sinh ML. Whew. It's even long to write, right? Okay. But hey, it's a solution. It's long, so what? I'm not afraid of long. Okay. So it's just putting numbers. I think in your calculator, you even have the sinh and cosh function, right? Feature, right? Do you? I have a worse calculator. I guess it's on my phone. I don't have a calculator. You're supposed to have a scientific calculator, right? Could you check it? Do you have this feature there? You might need to do some calculation.
I think you have to find it in the catalog, but it's not readily available.
Okay. So find a way. I think you can even Google it. Google, you can put in number, they can calculate the sinh and cosh for you. Okay. But you need it. Okay. That's why your engineer gonna get paid big bucks for your job. Okay. That's not everybody can do. Okay. Okay. Any question? This is the case 2. I need one more page for case 3. Do you still remember what is the case 2 condition? See if you pay attention.
Finite length on the fins, where there's convection at the end for
That's
case
right.
2.
That's right. That's a case 2. Okay. Unfortunately, case 2 is a very practical case, but it's the longest in the solution. Okay. Okay, let me give you case 3 then before I give you an example. Oh, I think I have something else to cover for the example before the example. Okay. Case 3. Case 3, the temperature theta over theta O equals, it's much better. That's people try to use case 3 for many of different applications. They think it's easy to apply. Cosh M times L minus X, and that's it for the numerator. Denominator is also cosh ML. That's it. Okay, that's much easier to do. Okay, that's why in practical, a lot of case actually is 2, but people think it's okay to apply case 3, okay, because the loss to the tip to the surrounding, loss of heat through the tip to the surrounding is minimal. If it's minimal, it's just equivalent to the insulated tip, okay. But most of the time people don't apply case 1 because it is really not infinitely long thing, you know, it's not very long. So 3 is the most popular case, I think, from my actually experience. Okay, although the textbook doesn't say that, but when you talk to the field engineer, the real-time practical, you know, applications, people use the case 3 a lot because it's easy. Okay. And it's reasonable. It's not that inaccurate. Okay. And then the Q, heat transfer for case 3 is equation 2.36. Okay, it's H P K A. Oh, this is tench. Man, I don't know how to pronounce this. Is that tench, 10H or? Yeah, let's say tench. So what is a tench? Okay, let's look at, I think in the textbook it shows tench means sinh divided by cosh, right? Just like tangent is sine divided by cosine. So you probably need to find out calculate the sinh first and calculate the cosh, then 1 divided by the other is tench. Okay. So this is the case 3. Okay, obviously looks like much simple way. Sometimes you have a transfer. If you already have the M calculated, notice M is what? M is square root of HP divided by KA, right? So some people, practically, people use this. M times K times A. Oh, I think I missed something. Missed a theta 0 here. Always have the base temperature. Okay, it's outside the square root. Okay, just like the similar form like the previous one. You have square root of HPKA times theta 0 base temperature. Okay, then times long form. Same thing here. I'm sorry, I didn't write. The square root ended on HPKA. Theta 0 is next term, then tench. Okay, that's for the Q. So also people using this. Okay, it's up to you, it doesn't matter. Look at this, it's the same thing, right? If you M is this times KA, what happened? You move KA inside, it will be HP KA K square A square. The square can be canceled, it will be equals to square root of HP KA, right? That's the same thing. Same thing as this, okay? So this is exactly M times K times A will be exactly the same as the square root of HPKA. Okay, because anything problem, when you start it, you have to calculate the M, no doubt. M is definitely absolutely necessary. So you already have the M, why not just use this form? It looks like a little bit simple. You don't have to do square root. M times Ka, okay? So it's up to you. Square root of HPKA always equals to M times Ka. Some engineer might just remember that, memorize that, okay? It's a little bit easier in calculation. Hey, listen, it's easier in calculation is really important in this topic. Okay, you see how complicated the calculation would be, right? For this type of problem. A little bit simple process, save you some time and save you, from making mistake in the calculation, okay? So that's why people do that. Okay, I guess that's it for the solution part, okay? Now, thing, you have 3 different cases. So when you look at each application, you have to identify here which case I'm gonna use, okay? If you pick case 3, for example, then you have the temperature and then you have the heat transfer, total heat loss, okay? For that thing, it's easy. Then it's all about the calculation, okay? If you pick 2, unfortunately, you're gonna go through a little bit longer calculation process, okay? Be careful, don't make mistake. Remember, you got paid for doing these things. Don't do it wrong. People are gonna come back to sue you if you do something wrong, okay? So, okay, so I guess I have a couple minutes left. I don't wanna go to an example which cannot be finished today. So I gave you some example Monday, okay? But today, I'm just introduce the theory of the thing, okay? Starting from the general differential equation, use dimensionless, use the reference temperature theta instead of the temperature T, okay? Then we get the general solution. And this is the general solution. Then we have 3 types of boundary condition, case 1, case 2, and case 3. Okay, based on the 3 types of boundary condition, we have 3 sets of result of temperature and the total heat transfer from the thing. Okay, so that's the entire picture. Okay, I just want to make it simple to you. I'm teaching my philosophy. I want to make the topic, no matter how long the textbook write, I want to conclude it into a simple way for you to actually memorize it during the class. Okay, I hope you can do that. Okay, any question before we go? Is that good? Okay, seems like quiet. Good. So happy Friday and have a nice weekend. See you on Monday.
You too.